For decades, physics has been kind of stuck, you know? We've been staring at some of the biggest puzzles ever. But what if, just what if, one single radical new idea could come along and fix it all? Well, today we're diving into a theory that claims to do just that. It's called the single bulk framework, and it's a real challenger to, well, everything we thought we knew. So here's the deal. Our best theories, the ones that have been rock solid for ages, they're starting to show some serious cracks. We're seeing things that just don't add up, from the lifespan of particles not matching up to the universe expanding at different speeds depending on how you look at it. It's weird. And the folks behind this new framework, they're saying we can't just slap a Band-Aid on it. Nope. We need to tear it all down and build a whole new foundation.
Okay, so before we get to this wild new solution, we gotta really understand the problem, right? Let's take a closer look at these cracks in our understanding of the cosmos.
We're talking about some major head-scratching problems here. For example, you've got the neutron lifetime anomaly. Neutrons seem to live longer in some experiments than others. How is that possible? Then there's the Hubble tension. The universe is expanding faster right here in our neighborhood than it is way out there. That shouldn't be happening. And then you get to the really big mysteries. What even is dark energy? Why do fundamental particles have the specific masses they do? And the biggest one of all, the cosmological constant problem. Our theories predict the energy of empty space should be a 1 with 120 zeros after it, bigger than what we see. That's not just a small error. That is the single biggest mistake in the history of physics. These are not tiny little details we can just sweep under the rug. So how do you even begin to tackle all that? Well, the single bulk framework, let's just call it the SBF, comes along and says, hold on, what if we're thinking about this all wrong? It asks you to throw out the whole idea of empty space with little bits of stuff flying around in it. Instead, I want you to imagine the entire universe is made of one single unified substance.
And this is the core idea. They call it the granular vacuum. So picture this. The universe isn't a void. It's not empty. It's actually filled, completely packed with these incredibly tiny, fundamental grains. Think of it like a giant tub of sand, packed so tight that it's right on the verge of shifting. You know that moment when you add one more grain of sand to a sand pile and the whole thing just goes? An avalanche? That's the idea. The entire universe is in that state, constantly on the brink of an avalanche. And that's it. That is the fundamental claim. The entire universe is just this one granular material sitting at this critical point. So everything we see, all the particles, all the forces, even you and me, we're not separate things. We're just vibrations or little knots or waves traveling through this universal sand pile. It's a completely different way of looking at reality. So you might be thinking, okay, a universe made of sand, got it. But where do the laws of physics come from? Well, according to this theory, it all comes down to this one number, z, which is about 14.4. This is basically the average number of neighbors that each tiny grain is touching. That's it. This one little geometric fact about how the sand is packed together supposedly dictates everything else. All the rules, all the constants. The theory claims it can derive them all from just this number. It's a huge claim. So does this universe of sand idea actually hold up? I mean, it's a cool story, but does it solve anything? Well, here's where things get really wild. The SBF says yes. It claims it can take that one number, z, and knock down all those big unsolved problems one by one.
All right, let's look at the evidence. First up, particle masses. You see, in our current standard model, we don't know why particles have the masses they do. We just measure them and plug the numbers in. They're just random inputs. But the SBF says, no. It claims it can calculate these masses from scratch just by looking at the geometry of these little knots in the vacuum. And get this, its predictions for the masses of the muon and the tau particle are off by less than 0.5%. That's shockingly accurate for a brand new theory.
And it doesn't stop there. It gets even better. The theory then goes after one of the crown jewels of physics, the fine structure constant. This is a super important number that basically sets the strength for all of electromagnetism. And again, the SFB derives it from its sand pile geometry, and its prediction is off by less than 1%. This is a number we've known with incredible precision for decades, and this theory just spits it out from first principles. That's a big deal.
And this is where you really start to see the power of the idea. All those other huge problems, the SBF has a mechanical explanation for them. Dark energy? That's just geometric frustration. Basically, the grains can't pack perfectly, creating a background stress that pushes everything apart. The Hubble tension? They call it vacuum dilatancy. It's like when you step on wet sand at the beach and a dry patch forms around your foot.
The vacuum does the same thing around big galaxies, making space look like it's expanding faster. And that weird neutron problem, it's chalked up to vacuum yield stress, the idea that the vacuum itself can break or yield under certain conditions. Suddenly, all these disconnected mysteries seem to be, well, different sides of the same coin. It's all just the mechanics of this one granular substance.
You know, the holy grail of physics has always been to unify the four fundamental forces. The SBF's approach? It says those forces aren't fundamental at all. They're just different ways you can stress this cosmic sand pile. So gravity? That's just the whole thing stretching. Electromagnetism? That's a twisting stress. The strong force that holds atoms together? That's pure tension. And the weak force? That's like a little slip-up, a defect in how the grains are packed. 4 forces, 1 material. That's the claim.
Okay, so we have this wild new challenger in the ring. The big question is, how does it really measure up against the heavyweights? Let's put it head-to-head with the standard model and string theory.
First up, the standard model. The SBF's main argument here is that it's just cleaner, more elegant. The standard model is amazing, but it has something like 19 different numbers you just have to measure and plug in by hand. It feels a bit clunky. The SBF, on the other hand, claims to derive these things from its one core principle. For things like dark energy, where the standard model needs some crazy, unbelievable fine-tuning, the SBF says it just pops out naturally from the geometry of the vacuum. It's the difference between a beautifully designed machine and one held together with duct tape. Now, what about string theory? This is where the SBF lands its biggest punch. Its killer feature is that it's testable, like right now in the near future. String theory makes predictions about things at insane energy levels we'll never reach. SBF makes predictions we can check in the next decade. Plus, it avoids string theory's biggest headaches. There's no landscape of 10 to the 500 possible universes to get lost in. SBF says there's just one. And it doesn't need this thing called supersymmetry, which is an extra layer of particles that frankly we spent billions of dollars looking for and have found zero evidence for. And that brings us to the most important point of all. Because a theory, no matter how beautiful, is useless if you can't test it. And this is where the single bulk framework puts its money where its mouth is. It makes one very specific, very bold make or break prediction. A prediction that will either confirm it in a huge way or kill it, dead. So here's the timeline. This is how it's all going to play out. Right now, and for the next few years, scientists are going to be digging through old data looking for clues. But the real main event, the title fight, is scheduled for 2032. That's when a satellite called LightBird is set to launch. And by about 2035, we should have the answer. We'll have a verdict. So what's this LightBird satellite going to be looking for? It's going to be staring at the oldest light in the universe, the leftover glow from the Big Bang. And here's the prediction. The SBF says that if the universe really is made of these little grains, it should have left a unique fingerprint on that ancient light, a very specific sawtooth pattern. If space is perfectly smooth, like Einstein thought, that signal won't be there. If space is granular, it has to be there. It's a smoking gun.
And this right here is what makes it so thrilling. It's a clean test. There's no wiggle room. LightBird will see one of two things. Either it sees that sawtooth pattern, which would be a game-changing confirmation. I mean, Nobel Prizes all around, a new era of physics begins. Or it sees a perfectly smooth signal. And if it does, the theory is just wrong. Done. Falsified. It's back to the drawing board. This is how science is supposed to work. It's beautiful.
So when you boil it all down, the people behind this theory aren't just trying to make a better map of the universe. They think they've found the keys to the terrain itself, a description of what reality actually is. And the next decade is going to tell us if they're right. We're about to find out if this is the path forward or just another dead end in the search for a theory of everything. The universe, it seems, is finally about to show its hand.